we start discussing about the force due to current carrying conductors. In external magnetic field. See, for this particular case, no, we don't have any derivation in textbook. Also, in board examination, it is very rare. Okay, it is not a frequent question, but we still see how it is derived. Okay, actual formula. Suppose a current carrying conductor of length L, current I, and placed in magnetic field B. Okay, the force experienced by the conductor is equal to B I L sin theta. Here, theta is the angle between the length and the current, the direction of the current.
Yes.
See, this equation actually it is similar to F is equal to BQV sin theta. This is the force experienced by the charge. Using this BQV sin theta, the actual equation is derived. Now we'll see one by one how it is there.
Okay.
Now consider we have a coordinate system X, Y, Z axis. So this one is X, Y, and this is Z. Now the current carrying conductor, it is placed in XY plane. The conductor is placed in XY plane. Okay, along XY plane it is placed, and the current is flowing in this direction. The direction of current it is in this direction. This is the direction of current. It means that in the opposite direction electrons are moving. Okay, we just mark the direction of electron. So electron, it is in the opposite direction. So this is the direction of electron. It means that the drift velocity is in the opposite direction. Drift velocity. Okay. Now suppose you just imagine charge is placed in this point. Okay, it is experiencing the velocity in the opposite direction of current. So this arrow mark, upward arrow mark is velocity, and this downward is direction of current. Okay, now the angle between, and one thing in the y-axis we have magnetic field. Magnetic field is along y direction. It is pointing in this direction. Okay, using the laws, Fleming's law, right hand rule. So this direction is, this is the direction of current, and the angle between the magnetic field and the current is theta. Okay, this is what we had in the final equation. So angle between the magnetic field and the direction of current, it is theta. Now see, as a whole conductor, it experiences a force. Okay, what actually happens now? We know this equation, this one. See, this equation is like a charged particle, a charge is exactly an electron. An electron experiences force, magnetic field. So external magnetic field experience a force which is BQV sin theta. Okay, here the velocity is the drift velocity. So now assume a single electron experiencing a force minus E Vd cross B. This Vd cross B. Why? Because it is a negative. Electron is negative. A force experienced by a single electron. But if you see the conductor, the entire conductor having a dimension, length L. Okay, the length of the conductor is L and area of cross section A. Okay, length is capital L and area of cross section it is A. Okay, across its volume it has n number of electrons. Okay, n number of electrons is contained in the conductor. Okay, the number of electrons in the conductor is capital N, which is equal to the number density into volume. In current electron, small n. In drift velocity, NA EVD, in that particular equation we use small n. Don't confuse this with the quantum of charges. Quantization. Okay. Now, if you see the conductor has capital N number of electrons. Okay. Also, they spread across its volume. All the electrons they spread across in the volume. When it is placed in the magnetic field, as a whole material, as a bulk matter, it experiences a force. So all the electrons will experience force in the same direction. Okay, as a result, the entire conductor will move in the direction of F. Okay, the conductor will experience now a force. This is the result of all the electrons experiencing the force. So based on Fleming's rule or the actual cross product rule, the direction of force will be in the Z axis for this case. The direction of force in Z direction. It is in the Z direction. Direction of force. Because here it is current and here it is magnetic field. So obviously it is in the upward direction, that is Z. Okay, now we'll go for the derivation, actual derivation. Therefore, the total force acting on the conductor is equal to N times F. Is it okay?
Yes, sir.
N times here. Okay, now insert the values. Okay, value of capital N and the small f. So F vector becomes NAL and minus E VD vector cross B vector.
So can you say once
So
again what is small n?
Small n is number of electrons per unit length, per unit volume.
Okay.
Unit volume. Check chapter 3.
No.
Chapter 3, drift velocity section. There we discussed this topic. So don't confuse with the total charge equal to Ne. That N is capital N.
Okay.
Q equal to Ne we discussed in the first lesson, but here the N is capital N, not small n.
Okay.
Okay, now we have to rearrange this equation. Okay, it is like they are rearranging the terms as well as the symbol, negative symbol. Okay, now see L and VD is taken inside and E is taken outside. Now see the L is taken closer to VD. So N, A, E is they are taken out. So minus L VD, it is combined now. Okay. Now what happens now? We have some small consideration. Okay, based on the vector rule, we know the current and drift velocity relationship. Current and drift velocity relationship. I equal to NAE VD. NAE VD. See, now compare these two equations. Compare these two equations. NAE and VD is kept here.
So I.
Yeah. We are going to replace this one. What happens now? We have some other consideration here also. What this means is IL vector. See, IL vector, it is current element. We already discussed. Current element. See, IL vector, it is in the right side direction. Drift velocity, it is in the opposite direction. See, whenever you see, whenever you discuss about current, it is not a vector quantity. Current is a scalar quantity. Therefore, if you want to write current in terms of vector, you have to multiply current with current element, the length element. Okay, I into L vector. See, whenever current in the forward direction, no, it means that velocity, it is in the opposite direction. So they are opposite. Okay, these are vectors and they have opposite directions. See, suppose if I write this term as VD is negative, it means IL is positive. You understand?
Yes, sir.
VD is negative, IL is positive. That's all. Therefore, minus LVD vector, minus LVD vector, it is written as VD L vector. A small consideration. Don't get confused here. LVD vector, it is written as VDL vector because they are opposite. They are opposite in direction. So the only confusing part is here. So LVD is written as VDL vector. Therefore, we just copy these terms again. So LVD. So replacing this equation, F vector becomes NAE. The VD is taken out, and L vector cross B vector. The entire term NAEVD, it is written as I. So F vector equal to I L vector cross B vector. That's all.
Okay, sir.
Or in case of scalar representation, or F equal to BIL sin theta. That's all. So don't give this symbol. What is that? A vector symbol for I. I is the scalar quantity. So theta is the angle between the direction of magnetic field, theta, angle between direction of current and magnetic field. See, even though current is a scalar quantity, when current is multiplied with the length, it becomes a vector quantity. IL is a vector quantity. Okay, now we have some special cases. Special cases, it is already we discussed. Whenever a trigonometric term comes, we have maximum and minimum condition. So F equal to BIL sin theta. It means that when theta equal to 90 degree, F becomes BIL maximum. Okay, it means that it is perpendicular. So when it is along x-axis, when the conductor is kept along the x-axis, you will get the maximum force. When theta equal to 0, it is parallel to the magnetic field, the force equal to 0. Force is 0. So when the conductor is placed along the y-axis, the force is 0. That's all. See, this application is used hereafter. So whenever a current carrying conductor is placed in external magnetic field, it experiences force. Okay, the direction of force, force is found using right hand rule. Right hand rule for the vectors. When theta equal to 90 degree, you may go for Fleming left hand rule or right hand palm rule. Already we discussed, I think, right hand palm rule.
Yes, sir.
See, this is for cross product. Cross product with an angle, any angle. Okay. Now next question is force due to two parallel current carrying conductors. So that question is board exam question. Force between two parallel long current carrying conductors. But for this case, no, there is no external magnetic field. The magnetic field is created between the two conductors. Okay, one conductor create magnetic field and the another conductor experience force. Similarly, both the conductors, they develop magnetic field as well as they develop a force. We will see one by one how it is happening. So this question is very, very important question. So here we are going to find force per unit length. So not exactly force per unit length we are going to measure. Why? Because the conductor is infinitely long. Okay, infinitely long. Therefore, we are just ignoring the length of the conductor. We are going for the force per unit length or force per meter. Okay, now we will discuss one by one. And for our consideration, the current flowing in the conductors in the same direction. And later we will extend for the opposite direction. Assume we have current carrying conductor. Current carrying conductor. See this, the distance between the two conductors there are. Okay, and the current is moving in the upward direction. Both the cases, same current. Okay, for our we will extend. Okay, we will go for same current at the end. Now we'll take I1 and I2. And this conductor is AB and this conductor is CD. See what happens now, the current flowing in the conductor AB produces a magnetic field. In a circular dimension. Okay, we will see one by one. இது கொஞ்சம் just make it closer because it is difficult to draw the diagram. Okay, now see the current flowing in the conductor 1, no, it produces a magnetic field as a concentric circle. The direction is concentric circle. Imagine we are taking this point. Okay, due to the current in this particular point, we experience a magnetic field which is looking like this. Okay, the magnetic field actually it encloses this particular conductor CD. Okay, I'll draw a little bit bigger. Okay, so this particular conductor AB, it produces a magnetic field and it extends up to the conductor CD. Therefore, the conductor CD, now it is in a magnetic field. Okay, this magnetic field, you assume this is B1. So the B1 is touching the conductor CD. Okay, therefore, the conductor CD experience a force. That force is F1. You understand? The conductor CD experience a force F1 due to magnetic field B1 and current because of the current I1. So therefore B1 is equal to, we know the magnetic field produced by current carrying conductor, which is equal to mu naught I1 divided by 2R. You know the formula. Due to a straight conductor is mu naught I by 2R. Do you remember?
Yes,
2R.
sir.
And according to the rule, right hand curl rule, okay, the current, it is in the upward direction. It means that the magnetic field will be like this. Okay, at particular point, the entire conductor CD, the magnetic field is point into the plane of paper. Magnetic field B1 into the plane of paper. Okay, into the plane of paper. Now we go for the force. F1 is equal to, we know it is P1 I2L. P1 I2L. I have to be very careful in choosing the number. The suffix values are very, very important. The force F1 is due to the magnetic field and the current I2, not I1. The magnetic field B1 is produced by I1, but the force is produced by B1 and I2. Now insert the values. B1 in F1, mu naught I1 I2 L divided by 2R. That's all. You understand?
Yes, sir.
Okay, now again repeat the same process. And one more thing, we have to draw the direction of the force. Now you go for the Fleming left hand rule or right hand palm rule. Okay, if I just take right hand palm rule, the four extended fingers, they represent the direction of magnetic field, and the thumb represents the direction of current. Okay, the palm will represent the direction of force. So using right hand palm rule, the force F1 is in this direction. It is towards left. F1 is towards left. You understand?
Yes, sir.
Okay, using Fleming left hand rule or right hand palm rule, F1 is directed towards left. Okay, now we are going to measure the force experienced by the conductor AB. Now the conductor, okay, we will repeat the same. See now what happens now, the conductor CD, it produces a magnetic field. A CD produces a magnetic field at this point. Okay, because of the current I2, there is a magnetic field surrounded by CD. It extends up to AB. Now the AB experiences a magnetic field B2. Magnetic field B2. A conductor AB experiences a force F2 due to the magnetic field B2. Okay, well. Now at this point, the magnetic field, actually again it is a curl. Okay, it is coming out of the plane of paper. So the magnetic field, it is coming out of the plane of paper. Okay, coming out of the plane of paper B2. So the B1 is B1 into the plane of paper. B2 is out of the plane of paper. Direction. I'll go for the magnitude of the force. So B2 is equal to, B2 is due to the current I2. Therefore, the magnetic field is mu naught I2 by 2R. I2 by 2R. Now F2. F2 is equal to, it is due to the current I1. Therefore, B2 I1 L. Now insert the values. F2 becomes mu naught I1 I2 L divided by 2R. You just consider this as equation 2, and the previous one as equation 1. Now compare 1 and 2, both are equal. Both are equal, and the direction of the force now. Again, now this is in the opposite direction. Okay, if you just go for Fleming rule. Fleming rule or right hand palm rule, it is again exactly opposite to the previous case. Previously, the magnetic field into the plane of paper. Now it is out of the plane of paper. Therefore, turn your finger. Okay, and turn your 4 fingers of your right hand towards you, and the thumb in the direction of the current, and the palm, it represents the force. Therefore, the force is in this direction. F2, it is in this direction. Right, towards right. So F2 towards right. It means that the two forces are equal and opposite. F1 and F2 are equal and opposite, right? Opposite in direction. And they are attractive nature. Attractive when the currents are in same direction. So these are all important points. When the current are in the same direction, the forces are attractive in nature. Okay, when the currents are in opposite direction, they will be repulsive force. Now 1 and 2. 1 and 2 are equal. The magnitude of the two forces are equal. Therefore, the force per unit length is equal to mu naught I1 I2 divided by 2R. That's all. Torque experienced by the current length. In magnetic field. Here it is uniform. Uniform magnetic field. That's out, and our coil, it is kept like this. See, for our simplicity, it is given as a full loop. Okay, practically it will not be looking like this. Okay, there may be some disconnections, and we have a complete circuit. I'll give names for the corners P, Q, R, S. P, Q, R, S. Length of the coil is, this height is, this length is A. A, and this height is B. B, therefore the area of the coil is capital A equal to AB, area of the coil. And this is the angle of rotation, or axis. Axis of rotation is passing through the center. Passing through the center, it is fixed. And the direction of current as per the textbook, no, it is in the downward direction from P to Q, PQRS. So the direction of current is along PQ RSP. So the current is flowing in this manner. And this one, PQRS, no, PQRS, it is a rectangular plane. Rectangular plane. The perpendicular to the plane, we have a normal vector. Perpendicular to the plane, we have a vector which is called the normal vector. Do you understand? This one, which is perpendicular to the plane of the coil. N. So N is normal vector perpendicular to the plane of the coil. And the direction of magnetic field, it is along this horizontal axis. So magnetic field, it is in this direction. So the green color, it represents the direction of magnetic field. So at this particular point, this is B. So the angle between B and N is theta. You understand where exactly B is located? So theta is located. So the plane of the, actually N is nothing but the area vector. It also represents the area vector of the coil. Okay, now understand the diagram clearly. Coil PQRS is kept in a uniform magnetic field. It has an area AB, and it is making an angle theta with a magnetic field. So the plane is not making theta with magnetic field. We have to be very careful. It is not plane that makes angle theta with B. It is the normal vector. Okay, normal and plane are in 90 degrees.
Okay.
Okay, plane. Sometimes they confuse with the term plane of the coil. Plane of the coil is not equal to the normal vector. They have an angle 90 degree.
Okay.
Okay. Okay, now we will see segment by segments. Okay, now see the length PQ. Length PQ, it is perpendicular to n vector, perpendicular to the magnetic field. PQ, the segment PQ is carrying current. Actually, it is perpendicular to B. Current is perpendicular to B. PQ means the current I only. Therefore, it will experience a force because it is not parallel, it is perpendicular. Therefore, this particular segment will experience a force. The length is B. B. Therefore, a force experienced by the segment PQ is equal to PQ is B B PIL, right? BBI.
BBIS or BIL, yes.
BIL. Instead of L, we have taken B. Okay. Here theta is 90 degree. Theta 90 degree for this case. Sine 90 degree.
Yes, sir.
Okay, sine 90 degree. And the segment RS.
Zero.
No. It is also perpendicular.
Oh.
RS is also perpendicular to B, but the current is in opposite direction. That's all.
Okay.
Current is in opposite direction. Again, the magnitude of the force RS is also BBI. Okay, but opposite to FP. But one thing, FPQ and FRS are equal, opposite, and not acting along same line. Not acting along the same line. It means they produce torque. Not acting along the same line. Hence they produce
Torque.
A torque. Okay, if the two forces acting in the same line means the net force becomes zero. And they are otherwise they produce linear motion, not rotational motion. Okay, now we'll go for QR and PS. The segment QR and PS. Actually, QR and the magnetic field. QR and magnetic field, they have some orientation. It is not parallel always. Sometimes they become parallel, but most of the time they are not always parallel. Okay, therefore, what happens now? The QR will experience force in one particular direction. At the same time, SP will experience a force in opposite direction, and they are equal, opposite, and acting along the same line.
Okay.
They cancel each other. The force QR and SP. We will see one by one. Okay, using Fleming rule. Using Fleming's rule. Okay, you don't need to go for the mathematical expression. You just tell it by in your words. Okay, using Fleming's rule, the forces FQR and FSP are equal, opposite, and collinear. Collinear means they are acting in the same line. Okay, along the axis of the rope, along the axis of the loop or the coil. So they cancel each other. Okay. And these
Yes,
these two forces, they produce torque. No, now we are going to measure the torque. Otherwise, you write this as first point and these as second point.
Okay.
Then it will be easier. Okay. Now we calculate the torque value. So expression for torque. We know the torque formula. Torque is equal to force multiplied by perpendicular distance. Perpendicular distance, it is a scalar form. Okay, scalar form. Now I draw a diagram. One more diagram. See this. This is the length A. Okay, actual part of the loop, length A. And now we are experiencing a force. Okay, in the previous case, I forgot to mention the direction of force. Here, the PQ is experiencing on force. Now, PQ as well as RS, they experience force. Now, we find the direction of the force. Using Fleming, again, Fleming's rule, magnetic field, it is, or using your Fleming left-hand rule or right-hand palm rule. Right-hand palm rule, if I use, okay, it is outward. Okay, if I use right-hand palm rule, no, in this case, the force is outward. You understand? A normal inward force equal to inward force. What, 1 minute. They have mentioned inward in the textbook. Then we will check it. Current in the downward direction must be outward. Okay, 1 minute. Checking the text again. Maybe. Okay, their representation is something different. To the plane. Okay, using Fleming left-hand rule, we just identify in what direction the force is represented. Downward to the plane. Actually, it must be in the outward direction. In the textbook, they mention in the SLR or a textbook, no, they mention it is inward, but it is wrong. Okay, the force must be in the outward direction. Force, it must be outward. Okay, the force must be outward.
Yes. Yes.
The force must be outward. For this particular case, no, Here the force is inward. Wait a minute. Outward. Okay, it is inward. In this particular case, it is inward. Force is inward. Okay, actually, they are not acting in the same line. They are not acting in the same line. Okay. They are equal and opposite, but not acting in the same line. But in our diagram, it is looking something different. Outward. Okay, otherwise I draw like this: outward in this direction and inward in this direction. Okay, then it will be easy. So it is outward in this direction and inward in the opposite direction. Therefore, it will experience a turning effect. Okay, in this direction. Turning effect in this direction. So this force outward and this force is inward. Now I'll go for the direction, the magnitude of the force. So one force in this direction, another force in this opposite direction. And magnetic field, it is in the horizontal direction. And one more term, magnetic moment they have mentioned. Okay, that we will come. Magnetic moment, magnetic field, and these are all forces. Forces and the length is A. Okay, now the perpendicular distance. Perpendicular distance is nothing but this one. This is the perpendicular distance. This one angle theta, and here also it is angle theta. So we need to go for the sine value of sine. This perpendicular distance is sine theta, A sine theta.
Okay.
Perpendicular distance, actually how they are easily calculating no perpendicular distance. One force it is in this particular direction, another force it is in this particular direction. Okay, this exact distance. This distance is called the perpendicular distance. This is R perpendicular. The distance between the two forces is called R perpendicular. Okay, now we'll go for the value. The force which is equal to PBI. Force is BBI, and the perpendicular distance is A sine theta. A sine theta. You take A inside, B, A into B, I sine theta. I sine theta. If there are n turns in the coil, n turns in coil, therefore the current is multiplied by n, torque becomes B, AB is capital A. AB is capital A, BA, NI sine theta. Because if there are n turns, the current will be multiplied by n. Therefore, the total torque experienced by the coil is NBA I sine theta. Okay. And we have one more term called magnetic moment. Magnetic moment, similar to the dipole moment we discussed in the first lesson. Magnetic moment. Magnetic moment M vector. M vector is equal to ANI. Magnetic moment is ANI. Okay. Now you just replace this term, these terms. Tau can be written as mb sine theta. mb sine theta. Otherwise, tau vector equal to m cross p. M cross. Okay. See, in this particular case, the direction of torque is it rotates the loop in anti-clockwise direction. Okay, it rotates the loop in the anti-clockwise direction. Okay, this is about the final expression. See, you just memorize the equation. Torque equal to NB IA sine theta or tau equal to MB sine theta. Is depending on the quantities given in the problem. Okay, we go for any one of the equations. So in galvanometer, we use this equation, not MB. Galvanometer will go for NBIA sine theta. Okay, for maximum force, already we know for maximum torque theta equal to 90 degree. Okay, therefore tau equal to NBIA. When it is 0 degree, when theta equal to 0 degree, torque is also equal to 0. So only we have two cases. See whether it is rectangular in shape or circular. Okay, it is applicable for both rectangular as well as circular.
Okay.
And circular loop. Both will experience torque. Okay, there is no difference. Current loop as magnetic dipole. See, in case of circular coil, of n turns, the magnetic field on axis. The equation is mu naught I r square divided by 2x square. That equation. Mu naught I r square divided by 2x square plus r square whole power 3 by 2. See, in case of x is very large comparing with the radius of the coil. If x is very, very larger than r, what will happen to this equation? X is greater than r.
We won't take R.
It becomes r becomes 0. Okay, r becomes 0. So x square plus r square becomes x square. Therefore, when you raise the power 3 by 2, it equals to x to the power 3. Therefore, the B axis become mu naught I r square divided by 2x power 3. And one thing you do, multiply and divide the equation by pi.
Okay.
Pi. The upper part becomes mu naught I pi r squared divided by 2 pi x power 3. Pi r square is nothing but area of the coil. So area of the coil is pi r square. So you just replace this one. Then mu naught I A divided by 2 pi
X cube.
x power 3. See, instead of pi, okay, we will do later. That also later also access. This quantity already I told you, magnetic moment IA.
Yes,
You
sir.
just change this with IA. Mu naught M divided by 2 pi x to the power 3, but multiply and divide by 2 again. We access, now it will become mu naught 2m divided by 4 pi x to the power 3. This is nothing but the magnetic field of a bar magnet on its axis.
Okay.
It means that the current loop is acting like a dipole. The value B equal to mu naught 2m divided by 4 pi x power 3 is the magnetic field along axis of a bar magnet. Bar magnet, which is a dipole. Moving coil galvanometer. First, what is a galvanometer? A device to detect current. The current is measured using ammeter, not galvanometer. Galvanometer, it is a very sensitive instrument. It only checks the presence of the current. Okay, sensitive instrument. Okay, even to a small current, it produces deflection. So therefore, we should not send any high current to the galvanometer. It will make the coil to burn. And the principle of the galvanometer. Principle of the galvanometer is nothing but this one. The torque experienced by the current loop in a magnetic field. This is the principle. Okay, when a current carrying a rectangular coil is placed in uniform magnetic field, it experiences a torque. So this is the principle of galvanometer. Now we'll go for the construction. What are the things present in the galvanometer? So galvanometer, it is a very important question. It is again based on a device-based question. Like we already studied a microscope, telescope, and then electrical devices like we meet Wheatstone bridge. Okay, now see what are the components present. Okay, we have a coil wound on a core. Okay, and we have a spring. Okay, spring, and then permanent magnets, and the coil is connected to a pointer. Okay, the entire setup is kept in a uniform radial magnetic field. See, this one is something different. Uniform radial magnetic field. Why? Because the radial magnetic field, it always give the magnetic field which is making angle 90 degree. Okay, the current, whenever the current flowing through the coil, no, it always experience 90 degree with the magnetic field. Otherwise, the plane of the coil is being parallel to the magnetic field, always parallel to the magnetic field. Plane is parallel. Therefore, the maximum torque will be experienced always. In the previous case, no, here it is something different. Whenever it is making turn, so the turn will produce some different torques, because PS and Q are they produce some forces in opposite direction, and therefore the torque will be something minimum. Also, the magnetic field is not always perpendicular to the current. Okay, this makes some angle difference. But this case, radial magnetic field, it produces strong torque. Therefore, the theta is always 90 degree in this case. And pointer is connected to the coil. See, whenever a current is flowing through the coil, it produces a torque. Therefore, the coil is turned. Okay. Along with the coil, the pointer is also moving. And we have a scale. The scale is actually, it is calibrated for a small current passing through the galvanometer. It produces some deflection. That deflection and the current, okay, they have some direct relationship. So the deflection produced in the scale as well as the current through the galvanometer, they have some relationship. Okay, based on that relationship, we can use the galvanometer as it is. Otherwise, we can make the galvanometer into ammeter as well as voltmeter. We will see the conversion also. Okay, what happens now? The coil actually, it is connected to the pointer. Whenever the current flows through, the pointer is now deflected. Pointer deflected, but if we don't have any special arrangement, if there is no spring connected, no, the pointer will be there in the final position wherever the current is left. Okay, after the flow of current, the pointer will move certain distance. When current is stopped, what happens? It will stay in the same place. Okay, it will not come to the 0th position. So that is why we are using a spring. Okay, the spring will bring the pointer to its original position. So that is why we have a connected spring. Otherwise, the coil will turn like a motor. Okay, whenever the current is continuously flowing, no, the coil will turn like a motor. So all these are prevented using the spring. Here they usually use phosphor bronze based spring, and the suspension material also they use phosphor bronze. Okay, now we'll come to the oscillation point. See, the current, when it is flowing, no, it produces a rotation. It means that the spring is experiencing a restoring torque. Restoring torque is produced in the spring, which is equal to the actual torque, electromagnetic torque. Restoring torque, we know the formula, already we studied in class 11. Restoring torque is some constant C times theta. Okay. We'll go to NCERT textbook. Sometimes they use C. Here they have used phi, K, constant K. Class 11, they sometimes use C.
Sir, in this which is a spring, like which is in the image?
Here, spring. Huh?
Okay.
Yeah, it is here. The spring constant K and the deflection phi. Instead of theta, they have chosen phi.
Okay.
Phi is the deflection. Deflection in division. Okay, not in angle, it is in division. K is it is like torsion constant. K is the torsion constant. Torsion constant. It is depending on the material. Here they use phosphor bronze. Which is having a very less amount of value. Constant is very less. Okay, with which this value K phi is equal to NB IA sin theta. NB IA sin theta. Also, we know sin theta is 1. Okay, just neglected because of the radial magnetic field. The theta is 90 degree always. So sin theta equal to 1. Therefore, K phi equal to NB IA. NB IA. Where phi is the division. See, you just memorize this equation. Depending on the requirement, whether we are going to check current per division or voltage or the 1 minute. Current sensitivity or voltage sensitivity, we will see one by one. Okay, you just rearrange the term. I is equal to K divided by NBA phi. Rearrange this equation. K divided by NBA. See, inside the bracket, all the terms are constants. Okay, K is constant, NBA, the number of turns, magnetic field, because it is a permanent magnet, and the area of the coil, everything is permanent. Okay, they are not changing over time. They are constant. This particular constant is called G, which is galvanometer constant. I equal to G phi galvanometer constant. Galvanometer constant. It means that I is proportional to phi. The current, it is proportional to the deflection. Current, when current is flowing through the coil, it produces a deflection which is proportional.
Okay.
Therefore, the deflection produced in the galvanometer is directly proportional to the current. And another one term, figure of merit. Figure of merit. This is what we do in practical class. Figure of merit is the current which produces a deflection of one division. In galvanometer. Okay, deflection of one division. Actually, a galvanometer, I'll show you what exactly we use in the laboratory. This kind of galvanometer.
Yes, sir.
Here you see we have 30 divisions. 30 divisions, and the rest position is 0 in the exact middle. In this one, here we have 30 divisions. See, out of all the 30 division, here figure of merit is the current required for the deflection for one division. So that is what figure of merit. Usually it is in the value in our normal galvanometer. No, it is 20 microampere per division. In our laboratory case, 20 microampere per division. Roughly, it matches in this range for this kind of galvanometer. Okay, next particular topic is sensitivity, current sensitivity. Current sensitivity is like you just go for the equation K phi equal to NBIA. So current sensitivity is the deflection produced. The deflection produced in the galvanometer when 1 unit current passing through it. Okay, 1 unit current. 1 unit current means 1 ampere. It means that phi divided by I. This is what current sensitivity. Current sensitivity is phi divided by I. Therefore, take the remaining terms out, opposite side. NBA divided by K. You understand? Current sensitivity.
Yes, sir. Yes, sir.
Next, voltage sensitivity. Again, this is also similar. The deflection produced in the galvanometer when one unit potential difference is applied across the galvanometer. Okay, here 1 voltage is applied and the number of divisions are checked. Okay, here it is nothing but voltage sensitivity is phi divided by V.
Okay.
Phi divided by I. We know Ohm's law formula. V equals to IR. V equals to IR. Already we have I. If you multiply with R, you will get phi R. That's all. Phi divided by IR. Therefore,
NBA by KR.
Yeah, KR. That's all. This is voltage sensitivity formula. So all these are for our problems. Okay, and current sensitivity. Current sensitivity depends on number of turns, magnetic field, and area of the coil, and inversely proportional to K. It means that we need spring with the less constant. Spring with less K is needed. Okay, because the denominator term, if it is very less, the entire product will be a bigger value. So we need more current sensitivity. Okay, next, sensitivity. Suppose if I increase current sensitivity by increasing N, okay, that I'll write separately. If N is increased, what happens? Current sensitivity will also increase.
Okay.
But what happens to voltage sensitivity? When N increased, no, correspondingly R will also increase by the same factor.
Hmm.
Okay, if N is increased, R will also be increased by same factor. It means that voltage sensitivity will remain same.
Hmm.
Do you understand?
Yes.
Yeah, this question they used to ask. So what happens to voltage sensitivity when current sensitivity increased by changing the number of turns? Okay, changing the number of turns reduces current sensitivity, but no change in voltage sensitivity because resistance it will balance.